All right, everybody, we are in for a treat. We've got a memorization test coming up. Hopefully you did not wait until the last minute, but knowing you guys, you probably did. So 16 slides we're gonna get through, all of which are graphs. There'll be another video that helps us memorize the equations or the formulas that are gonna be on the memorization test. So first thing you gotta know is how to sketch a graph of y equals a times b to the x, given some different criteria. So for both of these, a is going to be positive. For the first one, if you're told also that b is greater than 1, you have to know this is exponential growth. Exponential growth will look like this. To the left, it should clearly be getting closer to the x-axis. It should be concave up here. And then it should pass through a y-intercept of a, whatever a is. Okay, now it's going to just be a on the test, but we want to mark that that's a. For the next part, if a is positive and b is in between 0 and 1, it's going to be exponential decay. So to the right, so again, y-intercept is still a. To the right, it should clearly approach the x-axis, and my x-axis is kind of off there. And it's going to be concave up, so it's going to look like that. All right, so that's our exponential growth and decay. Again, you probably won't get both, you might get one. The next slide, graphing in log. So we're only going to graph logs when b is greater than 1. So I could write it like this, or I could say like just graph y equals log base 3 of x, or base 10, or the natural log of x. All of them will look like this. They're concave down. They all pass through 1, 0, because we're not doing any transformations on this test. It's just the parent function before it's transformed. No reflections, anything like that. And this should clearly be approaching the negative y-axis, right? You're getting closer to the negative portion of the y-axis. All right, so this is what log functions look like. And again, you'd have to sketch that. You wouldn't be given this graph here. You'd have to sketch it. All right, so I grouped two of these together here because they group together nicely. So we're going to graph sine of x. We're also going to graph cosecant of x after we've done sine of x first. You wouldn't be doing these on the same graph. You would be doing these on separate questions here. But so how do we graph y equals sine of x? So you have to know it starts at the origin. You should know your x-axis scale is all the points on the unit circle that are on an axis. So pi over 2, pi, 3 pi over 2, and 2 pi. So in other words, we're counting by pi over 2. So that's the x-axis scale. And the y-max is going to be 1. The y-min is going to be negative 1 here. And so 0 is again at 0, pi, and 2 pi. Right, this is the graph of sine. Most of you guys are going to have this memorized from the course. We'll get to cosine in a minute, but how do I then take this and graph cosecant? Okay, well again, and by the way, this is just one period. I could ask you to do another period either to the right or to the left. But how do we graph cosecant? Well, anywhere there's a 0 for sine, I'm going to put a vertical asymptote because it's going to be 1 over that number, right, the reciprocal. So 1 over 0 is undefined. It becomes a vertical asymptote. Anywhere we have a 0, this is how I'm graphing cosecant. All right. Anything that's above the midline, which here's the x-axis, is going to just flip up about this point. So this point doesn't move, but the rest of it just flips up. And then this point doesn't move. Okay, but everything below the midline is going to flip down. And so this would also just be one period. Again, I could ask for more of this here, but you'll be asked to do these separately. That's how I memorize these though. Okay, I'm thinking of unit circle stuff here. And then I'm just flipping everything either up or down, and the zeros become the vertical asymptotes. But I do want to just reiterate, you do not include, if I ask for the graph of cosecant here, we are not going to include the graph of sine. Okay, so like this isn't going to actually be in our answer. So you can draw it and then erase it, but this is what our final graph looks like right here. All right, same thing for cosine and secant. So we have to know cosine starts at 0, 1, and that the x-axis scale is pi over 2. Right, the y-coordinates just go 1, 0, negative 1, 0, 1. All right, so this is one period of cosine. Again, no transformations. We're not doing any of that on this test. Then secant. I'm actually going to extend the graph of cosine just to make this a little bit easier. There'd be a 0 at negative pi over 2, and there'd be one at 5 pi over 2 as well. So just to kind of make this a little bit easier, Anywhere that cosine has a 0, secant is going to have a vertical asymptote. So negative pi over 2 and positive pi over 2 and 3 pi over 2 and 5 pi over 2 if I was to go all the way over there. All right, anything that's above the midline, the x-axis, this point doesn't move, but everything else flips up. Okay, this point doesn't move, everything else flips down. All right, so that's how I construct secant. I don't, you know, if I just think about the secant graph, I don't necessarily have this memorized until I think of the cosine graph, and then I just flip it. All right, so again, you don't have to draw a cosine, but that's how I remember what this graph looks like. All right, tangent. So I've got the graph of tangent right here. To graph tangent, you got to know a few things. You got to know its period is not 2 pi like sine or cosine. The period is 1 pi, and it goes through the origin. Okay, so because its period is pi, I'm going to go half of a pi to the right and put a vertical asymptote, and half of a pi to the left and put a vertical asymptote. All right, and then the rest of this is just pure memorization. I know that it's to the left, it's going to be moving down, and it's going to be concave down. And to the right, it's moving up, and it's concave up. All right, so that's, again, this one is probably more just pure memorization. Cotangent is the trickiest one, I think, for most people. So I went ahead and just copy and pasted the graph of tangent. This is not the graph of cotangent, but I want to keep a few things in mind. Its period is pi, all right? Anywhere tangent has a 0, cotangent's going to have a vertical asymptote. So the first vertical asymptote is at 0, and because its period is pi, the next one is going to be at pi. Okay, that'll be the next vertical asymptote of cotangent. Anywhere that tangent had a vertical asymptote, cotangent's going to have a 0. I'm just going to do one period, so I'll put mine here, but there's also one right there as well. All right, and then the rest of this in this section, it's kind of like tangent flipped and moved over. So it's going to be concave up to the left, and it's going to be concave down to the right, like that. And so this, again, getting rid of this graph there in white. And this part as well. Okay, so this is the graph of cotangent. Even the vertical asymptote's not there as well. This is one period of the cotangent graph. All right, inverse trig function. So inverse sine. Inverse sine is literally just this part of a graph. We're going to have to get the scales right, and so I want to talk about how I remember this. So one thing that we memorized is inverse sine and inverse tangent are the right half of the unit circle. Inverse cosine is the top half. Well, the right half of the unit circle goes from negative pi over 2 to pi over 2. And so because this is inverse, on regular sine, the first x coordinate is pi over 2. That's going to be the first y coordinate right here. All right, and then over here, the first negative x would be negative pi over 2. That's now the first y coordinate down here. The y coordinates on sine would be 1 and negative 1. So those are now the x coordinates, 1 and negative 1. All right. If you forget this one on the exam and it actually shows up, you can just take your coordinate points from sine. So you have a coordinate point at 0, 0. Okay, just switch them. It's still at 0, 0. You can take the next point that's on the normal graph would be pi over 2 comma 1. You're going to swap them, make it 1 comma pi over 2. And again, this one's kind of tricky. You'd have to take the point negative pi over 2 comma negative 1 on the original sine graph. So this point right here, okay? And flip that one into negative 1, negative pi over 2. All right, but that's the graph of inverse sine. The graph of inverse cosine, remember cosine is the top half of the unit circle. Okay, I kind of think of it like, I'm just twisting that C, turning that C right there. All right, and so it's the top half of the unit circle that goes from 0 to pi. So none of this is going to be below the x-axis, right? It's going to go from y equals 0 to y equals pi. And again, you can take the coordinate points. This is the point 1, 0. It came from on regular cosine 0, comma 1. This is 0, comma pi over 2. It comes from pi over 2, comma 0. And this is negative 1 comma pi. It comes from the point on the original cosine graph of pi comma negative 1. So we're just switching these three and only these 3 points, all right, to get this inverse cosine graph. Inverse tangent. So regular tangent had vertical asymptotes at positive pi over 2 and negative pi over 2, so they were here. Now they're horizontal asymptotes at positive and negative pi over 2. The point at the origin doesn't move, right? When you switch 0, 0, when you switch 0 and 0, it's the same thing. And so we just have to sketch it towards the vertical asymptote, or sorry, towards the horizontal asymptotes from there. All right, so that's the graph of inverse tangent. All right, we're getting into polar now. For the polar ones, I think it's best if I give you guys a graph and you then write out a possible equation. All right, so I want to go through some different polar examples. So I've got a circle here. Circles are always going to be r equals a number times either sine or cosine of theta. All right, and so whatever this number is here, that's the number right here. So it's -4. And because it's symmetric about the x-axis, it's cosine, right? If this was, down here, right, it would be a -4 sine of theta, right? Or if it was up here, +4 sine of theta, etc. All right, so those are circles for polar. But we also graphed roses. And so these are our two equations for roses here. For both of these, b is going to be bigger than 1. If b is 1, it's a circle, it's not a rose. Okay, so b is going to be bigger than 1. It's going to be a whole number. All right. Keep in mind, anytime that a petal is on the x-axis, this is going to tell us that it's a cosine function. All cosine functions, so I can actually say that both imply each other here. If it's cosine, you've got to have a petal on the x-axis every time. If there's no petals on the x-axis, it's automatically going to be sine then. All right, so that's how we distinguish between these two. There will either be b petals or 2 b petals, depending on if b is even or odd. So this is when b is odd, there's b petals, and when b is even, there's 2 b petals. All right, so to run through some examples here. All right, so this is a rose with 3 petals. All right, so because there's 3, let me change this number. I like that. All this is going to be 3. So this is going to be 4. All right, so there's 3 petals here. All right, so b is going to equal 3 whenever it's an odd number of petals. That number is odd, so it's going to be right here. And it's got to be cosine because I see a petal that's going, symmetric about the x-axis right there. Part of it is actually on the x-axis. Okay, so if any petal is on the x-axis, cosine. Now, whatever this number is going to go right here. It is technically possible for it to be plus or minus. And we'll go over how to check that another day, but I'm not super worried about that right now. So I would accept this answer. This one actually is correct. When cosine, it's going to be whatever that number is right there. Okay. Also, don't be thrown off if there's like a bunch of little circles. That's just radius of 1, radius of 2, radius of 3, and now we have a radius of 4. All right, so that would be our answer here. Let's look at another couple roses. So we have one with 4 petals. So here B has to be 2, right? Because if I double that number, I would get 4. So if it's even, you can cut the number of petals in half to find B. So B is 2. Whatever the length is of each petal, so let's just say this is 5, it's going to go right here. And again, it's going to be cosine because there's a petal on the x-axis, at least one. It doesn't matter if they're also on the y-axis. If they show up on the x, it's cosine. All right, so this is our equation here. I did my best to draw a rose with 8 petals. It didn't turn out perfect, but a rose with 8 petals. All right, and so here B would have to equal 4, right? Number of petals divided by 2 gives us B. So B is 4. And it has to be sine because there's nothing on the x-axis, right? There's no petals on the x-axis. Okay, so it's going to be sine. And whatever the length of each petal is, there'll be a circle that makes it clear. Okay. Say that, the circle has a radius of 10, right? So there's going to be a 10 right here again. Might be a plus, might be a minus 10. But that's not the focus of what we're doing now. All right, so if you had one I didn't do for whatever reason, but if there's one on the y-axis and not the x, it would also be sine. Okay, so if you have a petal on either part of the y-axis, okay, but not on the x, it would also be sine. All right, up next, 3 different types of hearts. You don't have to know the names, so I'm just going to call them all hearts. Whenever you have r equals a plus or minus b times either sine of theta or cosine of theta, it's going to give us one of the three types of hearts. Okay, a is always going to be a positive number. We're going to view b as being positive even if it's a minus. The minus just tells us the symmetry. Okay, so whether it's a positive or negative, I'm going to always view b as being positive, a as being positive. Now, if a and b are the same number, so it's like 4 plus 4, 4 minus 4 cosine of theta, or 2 plus 2 sine of theta, etc., you're going to draw a heart that goes through the origin. Okay, you actually bounce off the origin when it's like this. If a is greater than b, so the first number is bigger than the second, again, these are always positives, it is going to be a heart, but it's not going to go through the origin. And I'll show you what that looks like in a minute. And then if b is bigger, it's a heart that goes through the origin with an inner loop. Okay, it's like a circle on the inside. All right, so let's go over some here. So this would be a heart through the origin, and it may not, depending on the scaling and all that, it might look like a heart, it might not really, but you can kind of tell it's heart-ish shaped, okay, and it bounces off the origin. All right, so whenever this happens, we know a and b have to be equal to each other. So they could be 1 and 1, 2 and 2, 3 and 3. I'll make these 3 and 3 here. I also know it has to be a negative because most of its symmetry is about the negative portion of the y-axis. And it also has to be sine because, again, most its symmetry is about the y-axis here. Okay, so that's our equation here when the heart bounces off the origin. Now, another one where we have a heart that does not go through the origin. Sometimes this top part can look flat, but it actually does curve like that. So another heart, but it does not go through the origin. So whenever this happens, the a number has to be bigger. So whatever a is, say it's 3, b has to be smaller, ignoring that negative. B is going to be 2 or 1 or whatever. Okay. Again, it's going to be a negative because it's mostly symmetric about the negative y-axis. There's more down here than up here. And it's sine again because of the y-axis symmetry. All right. I did my best. I can't really draw these. Well, we have a heart, goes through the origin, has an inner loop or a circle on the inside. So here, b is going to be bigger than a. So whatever a is, I'm just going to keep going with 3. B is going to be bigger than that. All right. The reason there has to be a negative is most of the symmetry is about the negative portion of the x-axis, which also tells us that it's cosine because of the x-axis here. All right. One more slide. Almost done. Longest video yet. You got to know the unit circle. Okay, no, it's not a graph. And I'm not going to go over the whole thing right now. There's plenty of YouTube videos out there if you're still struggling with the unit circle. I will say a couple things. Some of the most common mistakes that people make on the unit circle are not knowing at 0 or 2 pi that the coordinate point is 1, 0. They think it's 0, 1. This is 0, 1, negative 1, 0, 0, negative 1. The other thing that tends to happen is either people mix up their negatives or they actually swap the x's and the y's, right? So the next point, which is at pi over 6, we got to keep in mind square root of 3 over 2 goes first, then 1/2. And I remember that because to this point, you would go over more than you go up, and the square root of 3 is bigger than 1. Okay? So again, you would want to work on that, especially if you struggled second semester, like if you had a lot of low test scores. This might still be an issue. I wouldn't just take it for granted that we still have this memorized. All right, guys? So hey, don't wait until the last minute to study. Start studying now. There'll be another video with formulas. I know it's a lot. You guys can do it. Take breaks. Don't save it all for the last minute. You guys got this. And as always, stay flawless.